Okay, so last week we did the probability, and we know that the probability, the summation of probability must be equal to 1, right? So we did say any value of probability, it could be between 0 and 1, right? Max value for probability equal to 1, the smallest value could be equal to 0, and also the summation of all probabilities must be equal to 1. Okay? So today we'll start with the probability distribution. So now when we did study the variable, so the variable x, it might be any variable you are interested in, like, for example, the income. So this might be income. So, and all values here, it will be each single value of those will be observation. So let's say that the income is like, I don't know, 2,000 or 3,150 or so. So each single value of those we call observation, and the whole column we call it the variable. Okay, the variable it could be random if the value is determined by chance. So each outcome, it will be just totally random if we got determined that this value just basically by chance. So let's say if I have this x equal, or this variable equal the income, then what? Then must be this variable inside here. We have different values, right? So let's imagine that I want to take the income, and then I go out, take a sample, and start picking some people. Those, and each one I pick, just ask him your income, right? And register it down. So how can we get random variable for this one? It must be, so let's see, if I want to random about the income, and then I will say, okay, the income of people living in Orlando equal to some number. Okay, so I cannot go, for example, in front of hospital and still waiting for doctors to go out and then ask them. So this will be biased, right? So it will be, it will be random if we pick from different places, right? So for example, Walmart, like different level people, they go to Walmart, right? Or Publix, for example. Okay, and then I can get it. So those values, the values of observation must be different from each other. And the probability distribution is the behavior of that random variable. So when we find the probability distribution, we will know the behavior of that variable, how it will change over maybe time or over different values. So for example, the income. So let's say, for example, I want to do a relationship between two things, income and spending, right? So let's say X, the income, and Y will be how much you spend a month. Okay, so for sure, let's say that one income 2,000. Might be in my sample, I will get 10 of them, their income equal to 2,000, right? But the outcomes, I mean, the spending might be different. So might be I'll find the first one spending 800, and then might be the second one 1,900, and maybe 15, maybe, I don't know, two, using some saving maybe, or loan or anything. So each value of X might be, has a different values of income, which is, makes sense, right? 10 people, they have the same amount of income. Each one, they will spend, I have a family or not, how I go eat out or just eat at home. I take like frozen food or go to eating some fresh food. I don't know, right? So different from one to one. So this is the probability distribution. It will study the behavior of this random variable, how the random variable is going to be. Okay, so and this kind of distribution might be just a formula, or maybe formula, table, or a graph. So we have three things we can find in probability distribution. We will see them in a second. So table, formula, or graphs. So discrete, I think by now you already know the discrete. So discrete random variable, if the random variable can be, is countable, right? We did say discrete if it's countable. So if we study something countable or finite, countable or finite. So might be this number countable, 1, 2, 3, 4, 5, 7, 10, 15, 2 million, I don't know. So let's see if the variable is how many times I flip the coin till I get hit. So might be the first try, right? I get hit, stop. That's it. Might be I'll repeat the experiment twice to get the hit. And might be I'll repeat it 1,000 of times to get the first hit, right? So it's, but anyway, if even if I repeat it, in the end, this number will be what? Finite. Okay? Or do you remember the examples of shoe size? The example of shoe size is not countable, but finite, right? So can you say the shoe size is countable? I cannot count them because 7.5, I mean, it's not whole number, so it's not countable, but it's finite because we know that the shoe size, let's say, I don't know, from 0 till maybe, I don't know, maybe 22. I think the max, at least I did see, maybe 22, right? How many? 50, 60, 70, 100, then count. So even they are not the whole numbers, but finite. So countable, 1, 2, 3, 4, 5, 7, 10,000, or finite, some include some digits, but we have specific number. Okay, and continuous, anything we can measure, right? Distance, area, weight, temperature, all those variables will be continuous variable. Okay, now what is the requirement for random variable? We have three things. We must have them. One, numeric. That when we say this is probability distribution, that means we will have some, our variable X will include some numerical value. Numerical. That's numerical, which is what do we mean by numerical? It will be either discrete or continuous. Do you remember the 4 level of measurement? We have discrete, we have nominal, right? And then interval, ratio, and then ordinal, right? Ordinal, nominal. So ordinal, nominal, both those two is categorical data. So those two will not be included in our list. So we have two things. It will be numerical, which include two things, discrete or continuous. So this variable must be discrete or continuous. The values that the X will take will be discrete or continuous. So the first condition, numeric. The second one, summation of probability will be equal to 1. So when we take, so the distribution will be in this, like this will be. We have X here, and we have probability of X. And then we have, I don't know. So here, for example, then this one must be 4 to maintain the sum of 1, right? So the summation of those probabilities must be equal to 1. It could be 0.999 or 1.001 if we round. If we round, so imagine that when I got this X probability of X, the actual probability was 0.01347. And then I will round usually the probability to three digits. So this number, I will count just those, right? And then those will take them out. It will get me some error here, like this, okay? So first condition, numerical. The second one, summation of probability equal to 1. The third one is each single value or each single probability must be between 0 and 1. So those values here must be between 0 and 1. It's not acceptable that we have here, for example, here -2 and then here 0.6. Still 1, right? But since this value is negative, so this is not the probability distribution. Why? Because we have negative value here, okay? So three conditions. Numerical, summation equal to 1. Each single probability will be between 0 and 1. Okay, so let's see, look to this example. So now this is our variable. Our variable X is the number of heads. Let's keep it easy here. Just number of heads we get, okay? Okay, so can you tell me if we have 2 coins, if we have 2 coins, and then what's the outcome we'll get? So we have 2. Head. Yeah, so head, tails, or tail, head, and then tail, right? So this is our 4 outcomes. So now they said what? Number of heads. So let's see. The first one, how many heads we have here? 2. And then here, how many heads we have? 1 here, 1 here, 0. Okay? So now the values that this random variable will take, each single value here without repeating. So the values will be 0, 1, 2. Okay? So now this is our X. Let's do it here. So this is X, and this is probability of X. Okay. So the values we did say 0, 1, 2. Okay? And then let's say how many times this, so let's start with 0. How many times 0, how many outcomes we have here equal to 0? Here. 1. 1 out of 4. So it will be 1/4. What about 1? It will be 2 divided by 4. What about 2, 1? Okay, so now this is our distribution. Let's see, can we call this one probability distribution or not? Let's check our 3 conditions. The first one, numerical, which is those values. Numerical, right? So the first one, okay. The second one, the summation of those probability must be equal to 1, which is those. The sum of those values, right? Summation of Bx equal to 1, which is probability of 0 plus probability of 1 plus probability of 2, right? So it will be 1/4 plus 2/4 plus 1/4, right? Which is equal 4 divided by 4 equal to 1. So now the summation is equal to 1, which is, this is our second condition or second requirement. Okay. And then the third one is what? Each single value of those probabilities must be between 0 and 1, right? Each single value of those, this and this, must be between 0 and 1, which is okay. So now we can call this as probability distribution, okay? Which is here. This is the first one, numerical, and then the summation equal to 1, and all of this, all of these values between 0 and 1. Clear? Great. Okay, so we did say just the values of that x take. So yes, this is discrete. If we want to say this is discrete or continuous, yes, it's discrete. Why? Because it's counted 0, 1, 0, 1, 2. Okay, and then it has 3 values, which is, we did say the outcomes without repeating. So we have 0, 1, 1, 2, right? So we call 0, 1, 2 because 1 is repeated twice. So this is 1/4, right? And this is 2/4, and this is 1/4, which is what we did. This is the summation equal to 1. Okay, so now this is the first one, which is a table, right? We did say the probability distribution could be a table, which is this. Which is, if you remember when we did frequency distribution, is exactly the same, right? Relative frequency distribution. If you remember, relative frequency distribution is exactly this table, okay? And then the second one, this might be a graph. This distribution might be in a graph. So look to this one. This is just histogram, right? This one, histogram. The other one we did, if you remember, what we have here, we had here frequency. That's what. But here we have probability, so we call it probability histogram. Why? Because here in the y-axis we don't have the frequencies, but we have probabilities. Okay. So now, if you see that our table was this, right? X, probability of X, and we have 0, 1, 2, 1/4, 2/4, 1/4, which is this one, 20. This is right. So now, let me explain this a little bit more. So now this is histogram, right? And for histogram, if you remember, we did say, well, if we want to find histogram, we have to use the boundary, the real limit, right? So now how can we change this data to continuous? Because this is discrete. How can we find that this? Do you remember how to find the boundaries? We did minus 0.5 plus 0.5, right? So now this is basically, it will be like this. The first one, 0 minus 0.5, it will be negative 0.5 to 0 plus 0.5, which is 0.5, right? It will be 0.25%. And then the next one, 1 minus 0.5, it's 0.5. And then 1 plus 0.5 will be 1.5. And this is 0.50. The third one, 2 minus 0.5, it's 1.5. And then you remember it, right? So now this is the boundaries or real limit. So now if you see here, from here to here, this is negative 0.5 and this is 0.5. And this is 1.5 and this is 2.5. So now for the first one, which is this class, we will have this one, which is 25% here, 25%. And then the second one, which is from 0.5 to 1.5, it will be this part, which is what? 0.5. And then the last one here will be 0.25. So now, if we add those, this plus this plus this will equal to 1, right? This is equal to 1, right? The summation of those probabilities must be equal to 1. This is 1 is the area of those rectangles. So if you calculate the area of those 3, you will find this area equal to 1. Okay, so table, graph, the last one formula. So if you look to this formula, let's plug 0 in this one. Probability of 0 equal to 1 divided by 2. 2 minus 0 factorial times 0 factorials, right? So it will be 1 divided by 2 times 2 times 1, right? Because 0 factorial equal to 1, 2 factorial equal to 2, and then 2, which is this equal to what? 1/4, all right? Which is the same value here. So let's go with 2. Sorry, let's go with 1. So probability of 1, it will be 1 divided by 2, 2 minus 1 factorial, 0 factorial equal to 1 divided by 2. 2 minus 1, it will be 1 factorial, 0 factorial, right? Which is 1 divided by 2, right? Because 1 factorial equal to 1, 0 factorial equal to 1, and then we have 2, which is the same as this value here. And then if we did the last one, which is when x equal to 2, it will be 1, 2 minus 2, right? Because here we have x, right? 2 minus 2 factorial, 0 factorial equal to 1 divided by 2, and then 2 minus 2, 0 factorial, and then 0 factorial, which is, let me see. I think we have something not right. 2, 1, so let's look to the formula again. Oh yeah, we have 2 here. So this is x. So then this value is 2, right? So here 2 factorial. So it will be 1, 2 factorial is 2, 2 times 2 is 4, which is the same as this value. So now we can consider this formula is, since now we have those values 0, 1, 2, and when we add those values we have one. Each single value of those is positive, right? And we have numerical here, then those three conditions, right? The three required. So now we saw that we can represent a probability distribution using table, graph, or formula, okay? So let's look to this example. Can we consider this example here? Let's just look to the table. I don't need you to see anything else. Just the table. Do you think this is a probability distribution or not? No. Why? So this is not one. This one. What else? The first condition.
So being like the left eye contact those two numbers.
Oh no, I mean this. So that's let's for the second condition, the summation equal to 1, which is not valid. But the third condition, each values of those between 0 and 1, which is okay, right? So, but the first condition, we did first condition say what? Numerical. Are those numericals? No. So now we have two things not valid. This is not valid and this is not valid, right? So now we have those 1, 2 is not valid. So we can say that this is not random. This is not probability distribution because of two things. That the values that the random variable will take is not numerical, and then this summation is greater than 1. Okay. Yes, so this is the first one, is not numerical, and then the second one is the summation. Okay, let's see, look to this example here now. Discrete, continuous, or not random variable. Discrete, continuous, not random variable. The first one, the square footage of a house. So now, is it countable? It's the area, right? It's the area. So the area is continuous, right? So it's because we can have a photon point. I mean, it will not be the exact number, right? Since this variable will represent the area, then we will get some half a foot or something, right? Okay, so this then the first one will be continuous, and then the second one, the exact time it takes to evaluate 26 plus 62. So go back and check the variable, what the variable is. Don't look to the numbers just to trick you, those numbers. The variable is time, right? And the time, can you count it or can you measure the time? Yes, so then what? It will be continuous, right? The hair color of kids in the United States. So discrete random variable, continuous random variable, or not a random variable. So the first condition of the random variable is what? Numerical, right? So when we say random variable, that must be numbers. Is there any number we can get from the hair color? Hair color is nominal, right? It's not numerical. So this is not random variable. And then the number of peacock in specific county. Discrete, yes. So this is discrete. This is continuous, right?
So three doesn't have a variable.
Yes, because it's we cannot include. So when we say random variable, this one, random variable must be numeric. It's a must. Okay. So if we cannot represent it as numbers, then we cannot call it random variable. It's still variable, but not random variable. Okay. Or still we cannot. So because this one, if you remember this, the hair color, we call it what? Categorical data, which is nominal, right? So now we have two categorical data, nominal and ordinal, those categorical data. And then we have two numerical, which is discrete and continuous. Those discrete and continuous could be a random variable. The other two, no. Okay, so now parameters of probability distributions. Okay, so do you remember we did say any value from population, any value we calculated from population, we call it parameter, right? And then any value we calculated from sample, we call it statistic, right? And usually the parameter is constant and unknown, and the statistic known and variable. That's why we can call a statistic is as a variable. And if it's a variable, then it will have has probability distribution. Okay, parameter is constant, so we cannot have probability distribution of a constant, but the distribution can be defined using parameters. Okay, so now this is how can we define the parameters of probability, the parameter of probability distribution. The first one, mu, okay, which is the mean. So mu equals summation x times probability of x, x times px. This is the mean. And variance, and we call sigma square, it's summation or the distance between each single value of x minus mean square, and then times the probability of that variable, okay? And we can use two formulas to calculate variance. We can use this one and we can use this one. So this is easy if we have the value of mu equal whole number, like 7, 2, 3, and this will be easy if we have a mu equal 3.2 maybe, okay? But if you use this one or use this one, you will get the same answer. So basically, if you distribute this, will be x squared minus 2 mu x plus mu squared, and then multiply the vx inside, you will get, in the end, will go this form. Okay? So basically using this or this, you will get exactly the same numbers. And then standard deviation is what? Is just the square root of variance. Standard deviation is just the square root of variance. So if we have this as the variance, then if we take the square root of this, it will be just the standard deviation. Okay. And then the last thing here, expected value. And expected value is exactly the same as the mu. So mu equal the expected value, or let's say expected value equal mu. So expected value is just, we can call it E, just some like E will equal mu, or E of this variable X will equal to mu. So now let's see this example here. Okay, I have this here. So let's find mean and standard deviation for this. So now remember we did use this like this. We have probability of X. Yes. Do we have X? Yes. Do we have X times probability of X? No. So we have to find this, okay? So here, when I get X times probability of X. So the first one will be 0. The second one, 0.5. And the third one, times 2, 0.5. And then, now we have them. The next step, summation. So take the summation of those. So summation XBX will equal to what? 1. So now this is a mu. Mu equal to 1. Easy, right? So just mu is X times this X times probability of X. So we want to take each single value of X, multiply with to its probabilities. Okay. And then the variance. So let's see the variance now. We have probability of X over there in the same table. This table. Do we have probability of X? Yes, right? And then, do we have X minus mu? So we do the operation inside the parentheses first, and then we go to the square. Do we have X minus mu? No. So we want to now go to X minus mu. I thought I already have the table here. Okay, so let's do it here. I'm pretty sure that I have the table. Or let's do this. Okay. So we have X and we have BX. So 0, 1, 2, 0.25, 0.5, 0.25. And then we have XBX, which is what we did, which is 0, 0.5, 0.5. This is summation equal to 1. This is equal to 1. And then now what we want to get, X minus mu. What do you think X minus mu will be? Without calculating. We did this one when we calculate the variance, if you remember, for the random, for the, let's see. So now we have X mu equal to what? 1. So it will be, the first one, it will be 0 minus 1, right? 0 minus 1, 0 minus 1, negative 1, right? And then the second one will be 1 minus 1, 0. And then 2 minus 1, 1. The summation equal to 0 all the time. So this is all the time equal to 0. But we don't, that's the reason why we did calculate, we did square this value. So we did square this value because when we calculate just the distance to from each single value to mu, we got 0. So that's why we squared. So square those values. So it will be just x minus mu square. It will be the first one is 1, right? 0, 1. Just those values. Square them. The first one, -1, square 1, 0, and then 1. The total will be 2, right? And then still we have the last step we want to do now. So now we have this, we have to multiply those two together, right? This one times this one. So this times this. The last step here, I should, okay, we can do it like this. So this is x minus mu square times px, right? Which is this times this, without the summation for sure. So don't, so this times this. The first value will be this value times this value. It will be what? 0.25, right? And then the second one will be 0. And then the third one will be 0.25. Okay? So, and then take the summation, which is the summation of this column. Okay, the summation equal to 0.5, right? 0.25 plus 0.25 equal 0.50 or 0.5. So now sigma square will equal 0.5, which is this. Clear? So let's use the this formula now. So let's use the second one. Do we have mu? Yes, which is equal to 1, right? Do we have probability of x? Yes. Do you have x squared? No. So we have to find x squared. So x squared, just square those values. The first one will be 0. The second one will be 1. And then the next one will be 4, right? Which is 2 squared. Okay. And then now, what we're going to do, x squared times probability of x. So x squared times probability of x. Probability of x, which is this. So let's just bring them down. Probability of x equal to 0.25, 0.50, and then 0.25. So the first one, 0, right? So this times this, which is this part. The first one, 0. The second one, 0.5. And then the last one is 1. Okay? So now, let's go to this formula here. So the first part, is this, which is equal the summation of those, right? 1.5. So this is the summation, this value is summation x squared probability of x, which is then sigma square equal to 1.5 minus mu. Mu equal to what? 1, right? Square. So it will be sigma square equal 1.5 minus 1, which is equal to what? 0.5, which is as the same as this value. So using this formula or this formula will lead you to the same answer, right?
So you can do either one.
Yes. So usually if you have a whole number of mu, it's easier to use the first one. If you have 7.4 or I don't know 13.25, might be using the second formula. But yeah, both of them they will give you the same answer. And then you can use technology also, right? So you can go to StatCrunch or anything. You can find them easily just using technology. Later we will see how can you use or calculator maybe. Okay. So this is how to do the process here. So they put everything here. So yes, so mean equal 1, and then variance equal to 0.5. And then for standard deviation basically is just, so we have sigma squared equal to 0.5, then the standard deviation is just the square root of this value, which is here. Standard deviation is the positive square root of, so because when we take the square root, so sigma basically will be plus minus this, right? But just we will take the positive value since we know that standard deviation never be negative, right? So we'll take just the positive value. So when I tell you, okay, what is the square root of 4? No, it's 2 plus minus 2. Because when we take negative 2 times negative 2 will equal to 4, right? And 2 times 2 will equal to 4. So the square root of any number will be positive and negative. So, but since we know the standard deviation never be negative, so we will get just the positive value. Okay, so this is the, okay. Now, so I think since you will leave at 9, right? Maybe we'll not take break till 9. And then I hope that we will finish everything so you will not miss anything, right? And then we leave all together. If
this is recording.
Yes, I do like Zoom recording, so I will send you a link on Lisa too. So I didn't record it with Kaiser, but I recorded using Zoom.
That goes to Blackboard?
No. I'll send you link your phone message using message. I don't know. Maybe I'll put it like, I don't know, YouTube and send you a link, or just I put it in my iCloud and send you the link. Maybe iCloud. Just I put it in my iCloud and then send you a link, so you can watch it from there. Because it's the Kaiser is, I don't know, it's tricky for Zoom. It's easier. I think there is a way to upload it. I'll check if there is. I think there is a way to upload this video in Kaiser. I think so. I'll check it there. If not, I'll send you just the link. Okay. So now, so any value, I think we did this one many times by now. Any value less than this, we call it significantly low, and any value greater than mu plus 2, it will be 2 standard deviation, it will be significantly high. Okay, so those, okay, here, not significant, but any value greater than mu plus 2 standard deviation and less than mu minus 2 standard deviation will be either significantly high or significantly low. So let's see. We found that when we tossing two coins, the mean number of heads, so mu equal to 1, which is the same example we did, and standard deviation equal 0.7, which is the square root of 0.5, right? Use those results and the range rule of thumb to determine whether two heads is significantly high number of heads or no. So now what we want to find? We want to find mu plus 2 sigma, since they said high, right? So here we did say it's high if it's equal or greater than this value. If it's greater than or equal this value, then it's significantly high. And then in this question, they ask significantly high or not. So let's find this one. Mu equal to 1 plus 2, standard deviation is 0.7. So it will be 1 plus 1.4, then it will be 2.4. So now any value greater than or equal this value, it will be significantly high. But here they say two heads, then two heads is not significantly high. Okay, let's say it like this. So here, the number of heads 0, 1, 2, and so on, right? 3. So here we have 2.4, which is basically maybe somewhere here. So 2.4. So any value greater than this will be significantly high. But since 2 is smaller than 2.4, then two heads is not significantly high, which is, if when I explained here, might be it will be easier. It will be here. This value is 2.4, and 2 somewhere here, which is the value is not significant. Okay, so then 2 heads is not significant. Okay, so the significantly high number of heads are 2.4 and above. Then 2 is not significantly high. Okay, and then significantly high number of success, we can say X is significantly high number of success if the probability of X success or more less than 0.05. The probability. So now we discuss here the value itself. This is the value itself, the value of the variable itself. But here we will discuss the probability. So the probability that we will have X or more success must be less than or equal to 0.05. So if this is the case, we can say this X is high number of is a significantly high number of success. And the same way, we can say that X is significantly low number of success if we have X or fewer success less than or equal 0.05. So this is the probability. If we find the probability that X or fewer success is less than or equal to 0.05, which is that's mean the probability that those events could be happening by a chance. So we allow the margin of error till by 5%. If it's greater than this value, then we cannot say it's significantly high or significantly low. So this value, they said 5% it's just the value, might be smaller or greater. So usually if the study related to human being life, then this value might be 0.01 or even sometimes like 0.001 if it's not related to only one human life. So if it's only to one, maybe 0.01, okay. But let's say if they have like some systems in airplane. So the problem will affect like maybe 200-300 people, right? Then this value might get smaller too. Okay. Okay, this is the same. And the expected value. I don't know why I repeat this one. Expected value, this is, we did it already, I believe. I don't know. So the expected value is the same. We did say expected value of x equal to mu. In our case here, mu equals summation x times probability of x. Or expected value just equal the same value as the mean. Okay. Okay, then let's check now here. So the first one, is this a probability distribution or not? So now if we add those values up, let's see, I think yes, then the sum, so let's see, check then. The first condition, those values must be numerical, right? First condition. The value that the variable will take must be numerical. This one, number one. The second, summation of probability of x must be equal to 1. And the third one, each single values of those must be between 0 and 1, right? And the first and the third condition is clear. And then, but when you add those up, you will get the value f equal to 1. That's why I did the right yes here. Then the summation must be equal to 1. Find the mean. Find the mean of the, so mean will be equal to what? Mu equal to summation x probability of x, right? So we use the same way we did. We have probability of x. Do we have x times probability of x? So we have to find this value, x probability of x. Okay? And then just take this summation. So this summation equal to 1 for sure. And then this summation, the first value will be 0. And then the first value here, it will be 0.3 to 1. And then the second value, and then take the summation. If you take the summation, you will get this mu. Okay? Mu will be equal 1.633, and usually use 3 digits for the probability distribution. So all values for probability distribution just use 3 digits. And then for standard deviation, so standard deviation sigma will equal to square root of summation x minus mu square times probability of x. Or you can use this formula, which is sigma equal to square root of summation x square probability of x minus mu square. Now, in this example, for sure, if you use this formula, it will be easy. Why? Since the value 1.633, it's for sure it will be easier to use the second, or more accurate, let's say. The more accurate results, it will be using the second formula. If you did this one, it will get this value, which is 0.8. So if you want to do this, we have to find x squared first, right? And then we find x squared times bx. And then we will, so for the first two values will be the same, 0.3 to 1. And then the next one, we take 4 times this value, and then 9 times this value, find those values, add them up, and then put it here, minus 1.633 square, right? Okay, so this is the values here. So now if we, so this is what we need for, so if we add those, will be 1.633, is this value. And then for this one, it will be, I don't know. It will be, if we finish everything, we'll get this value, which is 0.8. And this, the example is written here. It's from your, from the homework. So, and then I think still we have, yeah, just those things. I think that, I don't know, maybe this is another example. Or, oh, this is not the right. So this is not the right example. It shouldn't be here. So this is after the second one. Okay, now we'll start binomial distribution. Just give me like 2 minutes. Yes. I had a class before this one, which is 4 hours, and then now this. So
You only teach here?
I teach.
The Melbourne class.
Yes, I do. I have. No, I did. I did it here today. Okay, so now we did know the probability distribution, right? And we say probability distribution can be introduced in three ways: table, graph, or formula, right? And we did know the requirement for each probability distribution. We did say the random variable must be numerical, okay? And then the summation of probabilities must be equal to 1, and then each single value or each single probability will be between 0 and 1. So this is the summary for the last time. So some distributions, we know them. So we have a lot of probability distribution. So any function we have with all three those requirements, it will be probability distribution. Some probability, we know them, we know their formula, and one of them we call it binomial probability distribution. So binomial probability distribution, one from very important distribution we will study. And then to say that this probability is binomial, we have some requirement too. So beside that three requirement, which is numerical, summation equal to 1, and between each single probability for each single value between 0 and 1, we have some other requirement. The first one, so this distribution depends on trial. So we have some trial and we have some events that we are interested in. So the first one, the first requirement, the number of trials is constant or fixed. So we have number of trials n. And n, this is fixed from the start. And so we will repeat this experiment 10 times, period. So we have that specific number. We cannot say, so when I said, if you remember the example a few minutes ago, maybe, that when I said when I starting like flip a coin till I get hit. So now the number of trials unknown, right? Because maybe it will be just one try and then we'll stop, or maybe it will be 100 and then stop, right? So this is not fixed. But here, if I flip a coin 10 times, how many times I will get hit, for example? 0, 1, 2, maybe 10, right? So this is the first one. The number of trials, fixed number of trials, okay? Then 2, those trials independent of each other. So each experiment will be, so now each trial we consider it as experiment, right? So each trial experiment, what's the outcome of this experiment? Head or tail, right? So is this second experiment related to first one? No, right? Because if I flip this coin and then I get hit and then I took the coin again, it's not related. If I get hit for the first one, it doesn't mean now I will get hit or I will get tail, right? So that's mean if the experiment, if the next experiment not related to the first one, that's mean those experiments will be independent. And this one important, if you remember, when we got those marbles or balls, then if we pick a ball, we must return that ball before we start the next one. Because if we didn't return it back, then the second experiment it will be affected, right? Because now, if you look to this example, how many, the total in half, how many marble we have? We have 6. If we take one and we didn't return it back, then we will have 5. And then the next probability will be affected, right? So now, 1, number of tries, fixed number of tries. 2, independent. Each experiment will be independent from the other experiment. 3, the outcomes must be classified in 2, success and failure. Head or tail. We are interested, if our X is number of heads, then that success is having a head. Failure is having a tail. Okay? So here the word success and failure, it doesn't mean that this is good and this is bad. It just means what we are interested in is success, and what we don't interested in will be failure. So if our interest, the number of students they fail in this class, they will be success. So success will be the number of students they will fail in this class. Okay? So success doesn't mean that's something good. Success is the event that we are interested in our study. So if our study interested in number of failure before we get success, then the failure means, in this case, failure means success for us. Okay? The last thing, the probability of success remain the same in all trials. So now if I say flip a coin, probability of success equal to what? Which is the probability of having head, for example, would be 50-50, right? 0.5. Okay, finish the first one. The second try, the probability of success is what? Still 0.50, right? Which is, that's what I mean by the same. Now for this example, having a green marble, the probability of having green marble is what? 3 divided by 6, which is 1/2. But if we took 1 and we didn't put it back, the probability of having green marble, it will be what? 2 divided by 5. So now the probability of success is not the same. So then if we have to select, that must be with the replacement. Select, return first, and then start the next experiment. Okay? So 4 conditions in fixed number of trial, independent, 2 outcomes, and then the probability of success remain the same. So we have 2 important things, which is N, which is this is sample size, and we have B, which is the probability of success. I don't know how to write success, so sorry. Yeah, I learned English at the age of 32, so sometimes, yeah, sometimes this. So I remember that, like when I came here, the first week, maybe they asked me to write a essay, to write 2 lines and a half. That's it. That's all English I know. So I know my accent sometimes is a problem.
What language do they use? You said Libya?
Yeah, Arabic. Yeah. So so we have like some sounds they don't. For example, ha, ra. So it's those for you. It's not easy, and for Arabic speaker, like for example, B sound, we don't have it. So sometimes you will hear me say people. No, but we don't have that sound. And S and T is not easy to put them in the same word for Arabic speaker. So if I have word with S and T, I will face some problems to say them. Okay, so those 2 here, we can call them the parameters of the binomial distribution. The most important values for B is probability of success, and then Q is probability of failure. And then B plus Q must be equal to 1. Okay, so Q is probability of failure, B is the probability of success. Okay, here, yes. So B is probability of success, and then Q is probability of failure. And then N is fixed number of trial. We did say that. So P is probability of success is just one trial, and Q probability of failure in one trial, yes. And so this is the definition of probability of X. This is probability. So this one, basically this one, that is like this. Probability X will take exactly a value of X, like this. Okay, so let's say probability of X equal 3. 3 among, like, I don't know, N trials. So let's say 10 maybe. Okay, yes, and then here they mentioned that success doesn't mean something good. It's success is just what we are interested in, the event we are interested in. Okay, so let's see this example. So let's here, this is with replacement. This with replacement mean independent. Okay, now when an adult randomly selected with replacement, there is 0.85 probability that this person knows what Twitter is. Okay, so now this value is equal to B. B equal to 0.85. And then, okay, suppose that we want to find a probability that exactly 3. So now that we're asking for X equal to 3, this is what we are, and this is the unknown of 5. So now we have how many trials? 5 trials. So this is N. N equal to 5. Okay, does this procedure result in binomial distribution or not? So let's see the 4 conditions. 1, fixed number of trials, which is yes, we have N equal to 5, clear. 2, what's the second one? So 1, fixed number of trial. 2, independent, which is, they said with replacement, so independent. 3, probability of success. The fourth one, probability of success is probability of success exactly the same from trial to trial, which is yes, right? There is. So here they say when we choose adult randomly with replacement, it's 0.80% that he will know what Twitter is, which is, that's me. We select the first one, ask him, he said yes or no, and then back, and then take the other one. So now the fourth one, I remember the third one, which is 2 outcomes, right? So now when we pick one guy and we ask him, his answer will be what? 2 outcomes, yes, I know, or no. So 2 outcomes. So fixed number of try, 1, independent, 2 outcomes, yes, I know or I don't, and then probability of success equal from trial to trial, constant from trial to trial. So this 0.85, when we choose the first one, and then when you choose the second one, they will be the same, okay? So this is, okay, then, okay, this is, yes. Okay, and then identify the value of N, which is we did 5, right? And then the value of X, which is equal to 3, and the probability of success P equal 0.8. And what about Q? No, B probability of success, probability of failure, which is must be a numerical, right? And we did say probability, that's mean must be between 0 and 1, right? So this is probability of success. And we did say P plus Q equal to 1. So now Q will equal 1 minus B, right? So Q will equal 1 minus 0.85. Then probability of failure will be 0.15. So those now the values they are asking for, right? So, okay. So number one, the number of tries 5 is fixed. And then the 5 tries independent because the probability of adults, the number of tries are independent because the probability of any adults knowing Twitter is, yes, is not affected by, yes, but yes. For each experiment, yes, I didn't mention this. For each experiment, so let's imagine, so we have bunch and we choose the first one. We ask him, do you know Twitter? Yes. Put him back, and then we choose another one. That next one, do you know Twitter? So the answer of the second one is not related to the answer for the first one, right? So that's been independent, and for any this one with replacement, it will be independent too. And for any treatment, any experiment with the replacement, the outcomes will be it will be independent of each other. And then the third one, so we said yes or no, right? So if he does know or doesn't. And then the fourth one, the probability is 0.85 is constant from trial to trial. And then the second one, which is n equal 5, x equal 3, n5, x equal to 3, and then q equal to 0.15. And we did those, right? Okay. Now, okay, it's very important to be sure that X and B both refer to the same concept. Yes. So X and B, they both of them, so here will be number of success. This is probability of success. So those two, they talk about the same concept. This is number of success, and then this is the probability of success. Okay. So now here, the number of people that they will say, yes, we know Twitter. And then this is a probability of people they say, yes, we know. Okay. Or even not, this is not the probability of people, not probability of each single person say yes or no. Because B, probability of success in one trial, which is each person we ask yes or no, the probability he will say yes equal 0.8%. So this is a probability of success in one experiment. This is the number of success. But those both of them, they must be in the same concept of success. Okay. Okay, this is important. So now, so we did say if we have this, it must be with replacement, right? Because if we didn't return the marble before we start the next experiment, then the probability of success will be changing, right? But they said if we take n sample size divided by n, which is the population size, and we did find this value less than 0.05, it's okay even if even the experiment is not independent, we can treat it as independent. Do you remember the example that when we did pick three adults from United States and we check if they smoke or not? So we choose just the three outside of how many, let's see, in 20,000, which is if the sample size in this case equal to 3, and if we have a 20,000, this value will be for sure less than 0.05. That's mean what? From the 20,000, if we pick one and we did ask him, do you know Twitter or not? And he answered yes or no, for example. And then we return him back, and then we take another one. It's rarely to have the same guy again. And then if we don't, instead of like 20,000, it will be 19,999, which will not make any difference, right? To be almost the same, because this number is big. So if the sample size divided by the population size less than 0.05, we can treat dependent experiment as independent. Okay? And this is the formula for binomial distribution. So this is binomial distribution formula. Okay? So it will be n factorial divided by x minus n factorial times n factorial. This is probability of success to the power x, which is the number of success, q, probability of failure, and this is n minus x is the number of failure. Okay? This is number of success x, number of failure x minus, n minus x. So this variable will take values from 0 to n. So if we repeat the treatment 10 times, x is number of success. So if we repeat the treatment 10 times, maybe we'll get 0 success. So head or tail, 10 times, we didn't get head at all of them tail. So number of success, 0. If we repeat this experiment, we got 1 head, then number of success, 1. The highest number of success will be 10. Because we repeat that treatment 10, the experiment 10 times, then the highest number of success we can get is 10 success, right? So this, do you remember this? This part. Right? So this is, we know this one before. So now n is the number of trials, how many trials, how many times we repeat our experiment. X is the number of success among n trial, and then P, probability of success in one trial or any one trial, because all of them is the same, and the Q is probability of failure. Okay. Okay, so now for the same example we did, we know n equal 5, x equal to 3, b equal, which is probability of success, and q probability of failure. So now probability of x equal to 3, it will be, let me just write the formula first. So bx equal to n factorial divided by n minus x factorial, probability of success to the power, the number of success, and then probability of failure to the number of failure, n minus x number of failure. And then x will take 0, 1 till n, okay? So now if we just plug 3, and then n equal to what? 5. So we have 5 factorial divided by 5 minus 3 factorial, and then we have 3 factorial, and we have probability of success to 3, up to 3, right? To the power 3. And then we have 0.15, which is to the power 5 minus 3. Okay. So if you do this, we have space here, and okay. If we do this, you will get this value. 0.138. Okay. So now the probability, if you pick 3 persons or 3 people out of 10, the probability that they will say, yes, we know Twitter is 0.13, almost 0.14%. Okay. So the probability of getting exactly 3 adults who know Twitter among 5 randomly selected adults is this value. So round up to three digits, okay? For probability all the time, 3 digits. And then we can use technology to find, so not all the time you have to find this. So it's using this one to be like, for this one might be easy, but later you will see some problems that it's not easy to do it manually. So now you can just go and use some kind of technology to find those values, okay? So then the first one also using technology. So you have, I don't know, maybe you have stat disk you can use. Stat disk, or I don't know, Minitab, so all those things. Let me see. I don't know it. Let me see. I think. Okay. So if this is stat disk. So I don't remember where exactly. Let me see. Probability distribution, one analysis, and then probability distribution, and then go to binomial. Okay. And then here, number of tries, how many number of tries we have in that question? 10. And then the probability of success was 0.85. Okay. And then just, if you have a specific probability, which is the value of 3, right? So now this is the probability we did. Let me, this is too small. Let me, this one, which is probability of X will be 0.0012. Y is different. So let me see. So let's go back here. What I did here. Oh, it's number of tries. We have 5, not 10. So we have n equal to 5, right? So let's go back. Oops, not here. Just adjust this to 5. Yes, now it's the same value, right? Here. 1.138. So if you don't give any value here, it will give you the list, all 5 values. So because we did try, how many tries we did? 5. So this is the probability of getting 0. So if you ask 5 people, this value is the probability that no one will say, I know Twitter, right? And then the probability that all 5, they will say, yes, we know this, we know Twitter is 0.443 or 444 it will be, since we're not rounded up to. So this is one of, you can use this one even in your assignment, right? So just understand the idea how to calculate it manually, and then for your assignment or your exams, you can use this technology. But make sure that every single value here must be between 0 and 1, right? It will be, since it's technology, it will be. But I mean, if you do it manually, make sure that the values between 0 and 1. Okay, so let's go back here. So this is using this one, which is stat disk. Now, so this is the 5 values we got here, which is exactly the same values here, like number of trial 5, and then probability of success will be this value. Okay. So now what about the significantly high and low? So let's see this example here. The number of trials here, how many? So 460. So we have n equal 460. And then they said, and 252 if them were won by the team. So X will be 252. Okay, so let's see here. Yes, so n equal this value is 460. Let me just go here. There were 460 in football games decided in overtime, and 252 of them were won by the team that won the overtime. The results. Okay. Okay, so they consider, like, they ask us if 252 wins significantly high or no. Do you remember that we did say if X success or more must be less than or equal to 0.05 to say it's significantly high, right? I think if we go back just to make sure, before the independent, before the distribution. So not this one, I think right before this. Yes, this one here. This one. Say that X is a significantly high number of success if X or more success will be less than or equal 0.05. Okay, so let me. So now to find the probability that X greater than or equal to 52, right? So we say this, if this value less than or equal to 0.05, then we can say this value is significantly high, right? Because we said X success or more, it will be less than or 0.02. So to find this one, we have a problem, right? Why? Because to find this one, n equal to what? N equal to 460. So X greater than 252, it will be all those values, be 252 plus probability 253 plus all the way to probability to 460, right? And each single time we will find the way we did for, if we want to do it manually, and each time. So now we have B equal Q equal 0.5. right? And we have n equal to 460. And let's see. So for the first one, if x equal 252, it will be this one, n 460 factorial divided by 460 minus 252 factorials times 252 factorials pro p, which is 0.5 time to the power x 252, and then this times 460 minus 252. And you will do this process for each single one of those, which is manually is impossible, right? So now we have to go and use technology. So now how can we use technology? We will not make it hard. Let's just go here to this one. So how many trials we have? 460. And then the probability of success equal what? No, the probability 0.5, probability of success. And then the value here we have 252. Okay, so let's evaluate, which is this value here. X or greater, it will be 0.022. Okay, so now if this value less than 0.05, then we can say that the value of 252 is high number of success, right? 0.05, which is this value is 0.02, which is less. Then this value is significantly high, which is 252. So let's go back here. So let's see here. Where is it? Which here the value is the same we did, right? 2 point over there. 0.224. Okay. Here. Okay, and then such as so less than this value, right? This shows that unlikely that we could get 252 or more wins by chance. Okay. Okay, so now if this value is greater than 0.05, we will say, okay, having 252 wins or more will happen just by chance. But if this value, as we explained, this value smaller than this 0.05, then having 252 winning or more, it's not unlikely. It will be just, it will not be just by chance, right? Then it will be, yes, it's significantly high number of success, right? So we did say if probability X will be greater than or 252 is less than 0.05, we'll see, okay, the probability is X is a high number of success, which is what we, this one.
So it's not significant.
No, it is. It's let's go back to the definition here, just to make sure. This one. So we can say that that's X is a significantly high number of success if probability of X or more success less than 0.05. So what we have here, X equal to 252. So X greater than or equal to 252, we find it is 0.02, which is smaller than this value, right? Then this X is significantly high number of success. Okay. This one. So the last one, how to use the table. Some of you know to use how to use technology. Maybe you don't need you to use the table, but just to know. Now, if you have, so now we have P in this example, P equal to 0.6, right? Because here it has 60% of adults believe in devil. Assuming that we randomly selected 5, so now N equal to 5, right? Which is fixed number of, use table A to find the following. The probability that exactly 3, so the first one, probability X equal to 3. So this is A. 3 out of 5 adults believe in devil. 2, the probability that the number of adults who believe in devil at least 2. So B will be probability X at least 2, which is greater than or equal to 2, right? So for the first one, now they said use table. So for table, so we have 3 things we need. We have N, we have probability of success, and we have the value of X. So let's go to the table. So we have N, and we said N equal to 5. So this is our N. Okay, and we have P, which is 0.6, this one. So now we will, for sure, we will look somewhere here in this column. Okay, and then the question, they said the first, exactly X equal to 3. So under this N, we will go to 3, which is this one. So this is our value. Okay, I know it's not really clear from here, but this is the, when you look to the table, I mean, I just took like screenshot from the table in the back of your book. So this is the table. So you need 3 things: N, B, and X. So those values is the values of X right here. I don't know if you see it or not. So this is X. So if we did so, it will find the probability equal what? 0.346, which is this one. Okay. And I mean, if you want to use the formula, it will be probability of X equal to 3 equal to 5 factorial divided by 5 minus 3 factorials times 3 factorial times 3 factorial B, which is 0.6 to the power X, which is 3, and then Q 0.4 to the power 5 minus 2. So if you calculate this, you will get this value. So now from the table, you got it. If you want to use technology also, you will have it here. So number of trials, 5, probability of success 0.6, and then the value of X will be what? 3, right? Is it X equal to 5? 5, 3.6. Okay. 5.6 and then 3. Yeah, yes. This is the value, which is 0.3. If we round it up, is 3, 4 would be this one 6. 3, 4, 6, right? Okay. And then let's see the second one. The second okay. So let's see. Probability x at least equal to 3. 2, sorry. So it will be bx equal to plus probability, or let's write it as like this. B2 plus B3 plus B4 plus B5, right? Right, this is the probability. So we have to find probability 2, 3, 4, 5. So let's see here. It will be still we have the same. Yes, this is B, and this is N, and then we have the values from 2 up. So we will add all those values together. So from 2, 1, 2, 3, 4. So now, if you look from 0 to 9, if you add those values together, it will equal to what? 1, right? So now, either we add this plus this plus this plus this, or just we take 1 minus the first 2 values, right? Using complement. Let's see it here. So probability 0 plus probability 1 plus probability 2 plus probability 3, 4, 5 equal to 1. So now if we want to get those, just we can take those 2 to the other side, which is will be 1 minus probability 0 minus probability of 1, right? Using complement, if you remember the complement rule. Or using technology, it will be here. Just if we put 2 here, evaluate, it will be this value. So x or greater. So that will be 2 or greater, it will be 913. Okay. So this is, it will be probability x, x greater than or equal to the value we did, which is 2, right? So it will be 0.913. Let's go back here and see. This one, right? So it will be 2, 3, 4, 5, or just go use technology to find this value right away. Okay. Now to find mean and variance and standard deviation for the binomial distribution, it's easy. So do you remember when we start, we said when we find mu, we did x times the probability of x, right? And we will do sigma, square root of summation x square bx minus mu square. So if we know that distribution and binomial distribution, easily we can find those parameters. So this and this we call parameter of. Okay. So mu is basically n times b, which is all the time known, right? So for example, if we go to this example again, mu equal n times b, which is n equal to what? 460 times b, which is 0.5, right? So basically, it will be 230, right? So mu will equal 230. Easy, right? How to calculate mu if we know that we have binomial distribution. And then for standard deviation, which is this, right? Here. This is standard deviation. So standard deviation, sigma, will equal square root of NBQ, which is equal square root of 460 times 0.5 times 0.5. Right? Which is, I don't know the exact value, but if you look here, I believe to be so here, a mu will be 230 grams, and then the standard deviation will be 10.7 grams. Okay, and then let's go back, see what else they're asking for. Using the range rule of thumbs to find the values splitting the numbers of when that are significantly high or significantly low. Do you remember how to find significantly high and low? So this is a mu minus 2 sigma, and this is a mu plus 2 sigma. So any value here, it will be significantly high. Any value here, it will be significantly low, and values in between, it will be not significant here. So we know that a mu plus 2 sigma equal to, a mu equal to what? 230, I believe. And then 2 plus 2 sigma equal 10.7. 10.7, yes. So if you calculate those values, you will get this number, which is, let's see it here. So now it will be like this. Mu plus 2 sigma equal to 251.4, and then mu minus 2 sigma, it will be equal to 208.6. So any value here will be significantly high, right? And then any value here will be significantly low. Okay, so let's see. But the last one is the result 252 over time wins in 460 games. I said grams. Later I said grams, right? So yeah, 8 hours. Don't blame me.
It's been a long day.
I don't know how I read the grams. So now games, yes. Unless I did write it wrong there, but it's games. So it's this, I mean, this file is ready, just I add some stuff on it. Okay. So now they said 252. What about 252? Is significantly high? Let's see. Yes, 252, it will be somewhere here, right? It was different. So 252, it will be somewhere here, which is greater than 251.4, then this value is significantly high. Okay, the result, wing significantly high because it is greater than the value of 251.4 grams in, yes. So a significantly high number of success, X I think it's repeated this one. We'll see it like in each single maybe chapter. So having X or more success, if we have this one, X or more success less than or equal 0.05, then we can say X is significantly high number of success. And it will be X significantly low number of success having X or fewer is less than or equal 0.05. Okay. So this is from the formula. So this part, which is how the count, how we count, this is half with exactly X success among in trial. And this is the probability of just only one particular trial. So now let's say take this one. So this is the distribution. Fx equal to n factorial, n minus x factorial b to the power x q to the power n minus x. And imagine that n equals just two values, 0 and 1. That's mean what? We will do just one trial. One trial, head or tail. So this is, let's say, X number of heads. So if we flip a coin and get tail, this number of heads equal to 0. Or if we flip it to get the head, then the number of heads equal 1. So just let's just plug them and put n equal to 0. What you will see here? F of 0. We'll see what? 0 factorial, 1, right? N, which is, in this case, n equal to 1, right? This one, n equal to 1, which is one try. So this is X. N equal to 1, which is we did one try. So n 1 minus 0, it's 1. Factorial equal to 1, right? Do you want to write it here? So this is 0 factorial, and then 1 minus 0 factorial, probability of 0, q of 1 minus 0. So let's see this one. Out of all these things, we will have just q, right? All the rest will be equal to 1. So 0 factorial 1, 1 minus 0, 1, 0 factorial 1. B to the power number, any number to the power 0 equal to 1. So just we have q, which is the probability of failure, right? But what I want to say here, or what I want to do, I want to just apply it. If you put x equal to 1, then we will get b in this case. So just apply it to this first part. Put 1 x equal to 0. It will be this. If we put x equal to 0 to this part, what you will have? 1, right? What about if we put x equal to 1? So it will be 1 factorial, 1 minus 1 factorial, and then we have 1 factorial. This one will equal to what? 1. So now if we have x equal to 0 and 1, we don't need this part anymore. So if x will equal to b x q n minus x, which is this part, which is one time. By the way, this is a distribution. We call it Bernoulli distribution. This is Bernoulli distribution, and one of the. So now, if we repeat Bernoulli distribution, in some books you will find just Bernoulli experiment or Bernoulli distribution. If we repeat Bernoulli experiment in independent times, we will get binomial distribution. This is you'll see it, I believe, in one of your homework, you'll see one of the problems. If you repeat this Bernoulli distribution in independent times, you will get this distribution. Because this results here, in each experiment, you have, in each one experiment, you will have this. And then this one related to how many repeat this experiment. So we say this is if you repeat the experiment one time, then you have Bernoulli experiment, which is this part. So each time you repeat the experiment, you have this. And then this one related to how many times you repeat this experiment. Okay, so then if you repeat this experiment n times, you will get binomial distribution. Okay. So let's finish this one maybe. Now we have this one. So let's see the question here. What is the value of mean and standard deviation? So let's see the question and let's just make sure that this is binomial distribution. Can you just look to the question and tell me, is it binomial or not? So assume that the different groups of couples use particular methods of gender selection and each couple gives a birth to one baby. So for each experiment, we have one baby, okay? Or each time we have one baby. The method is designed to increase the likelihood that each baby will be a girl. But assume that the method has no effect. So the probability of girl will be 0.5. Assume that the group consists of 56 couples. So now, how many? So the first condition of binomial distribution, fixed number of trials. How many number of the number of trials here? Constant. So the first condition, okay. Then the second, independent. So for each couple, if they got baby boy or girl, they will affect any other couples. Then independent. 2, 3. The outcome, 2 outcomes of the experiment, which is here. The outcomes will be in each experiment will be baby boy or girl, which is two outcomes. Then they say here, assume that method has no effect. That means the probability 0.5 will be equal all the time from trial to trial. So we said probability of success will be constant from trial to trial, which is here will equal 0.5 constant. So we have all requirement for binomial distribution. So easy, we can say mu equal what? NP, right? This is the probability. This is mu for. This is a mu for binomial distribution. So n equal to 56, and then 0.5, which is equal to divided by 2. 56 divided by 2. This will be 2, and then 16 divided by 2, 8, right? 28. So now this is the first one, 28 girls, right? And then the standard deviation, sigma, will equal square root NBQ, which is equal to, so we already know this, which is n, so it will be 28 times 0.5, right? Which is equal some value here. It will be the standard deviation, this, 3.742. Okay? And then they said, use the range rule of thumb to find the value splitting that. Okay, so now we will find this, right? Mu plus 2 sigma and mu minus 2 sigma. Values here significantly high, and values here significantly low, right? So now we have this value, those values will be mu, which is 28, plus 2, and sigma we got it, I believe, 3.742. 3.742, and we have here the same 28 minus 2 times 3.742. So those two values, there will be those values. So the values will be 20.6 and 35.4. Okay, and then they ask that the last C is the result of 38 girls a result that is significantly high or no? 38. Yes. Why? Because 38, it will be somewhere here, right? Because it's greater than 35, then yes. I think this is maybe, I don't know. I thought I mixed those examples together. So I just copy this one from. Yes, so this is this example should be for the first session. Yeah. Okay. So now, 8:50. So we have like, it's 9. We have 1 hour left. I think what I will do, since we will leave, we'll record it later from home, maybe tomorrow morning. I will record it and put it as, I'll send you the link to. So we don't miss. And also we have the class, we have to recovery that we missed in last week, right? So 4 hours. So I'll try like maybe to do like couple hours, record it, and then just watch them. If you have any questions, we can go through them again.
Do this one and then
I'll do this one, this session, and then we have 10-1 and 10-2. So well, maybe I'll do those 3 sessions. So this 10-1 and 10-2. I hope that I can do tomorrow morning. So I did them. I'll put that record, watch it. If you have questions, we can go through those questions in the beginning of the next class. Because the good thing that what I will do, chapter 10, it will be a correlation and regression. And we did good part of regression and correlation. Just we want to know how to calculate the function. But we did the correlation right. So last week, I believe, we did the definition of correlation, and we say the correlation does not mean causation. And we did how we know if we have like a correlation between some variables. So the most part we already done that. That what we don't done, what we didn't do is just how to calculate those functions numerically, and will be like examples. And I'll try to go very slow and explain everything. So I think when you watch them, maybe you don't need even. I mean, if you have some questions or concern, that we can go through them next class. But since now, if you wanna leave, then maybe I'll stop here. It's 9 now. Then morning, I believe. Yeah, by 11. By 11, I think I can do some of them. It will be not easy for me. And then I'll take some rest now because. Okay. So do you have any questions from today?
that's pretty, I would say easy, but it's easier than, that's more understandable than what last.
Oh, I mean,
last week's was.
so the chapter, so the week of probability, this is different. I know. Chapter 4, maybe the most confusing one in the whole book. Chapter 4. The next, everything, I think what we will take easier I will guarantee you that's easier than chapter 4. So if you got chapter 4, then everything else will be easy for you. But about the homework and the repeated questions, start with homework. If you see any questions repeated, just send me a message. Number 15 is the same as number 14, for example.
Just different numbers.
Yeah. I mean, same. If you say like repeated or redundant question, so almost the same, and you will repeat the word twice, then don't do that. Just send me number 15 is the same as number 14, and skip it. Don't answer, and you will get. And then I can go inside the system and remove that question. It will be, I think, maybe save some time. Especially some of them, I remember I took a statistic class, and then they have like, I don't know, it's the same as those number 40. And I remember that 6-7 questions exactly the same, just different numbers. And then we have to repeat them again and again. And I know that it's annoying. So if you see just any questions that you see, this, I did this one before, then just skip it and I'll take it from the system. Okay. I think
Appreciate it.
you're welcome.